Hello, welcome to a new video. Today we're in this problem called and Queen number 51, hard problem leak code. Um, yeah, I watched the video on how to solve it. I was kind of confused at first because I thought a queen was a king in terms of like how they move, where a king can only move one space up, one space diagonal, and stuff like that. So I thought I had the solution just by looking at the example, but apparently not. So I didn't really know how to solve the problem by myself, so I watched the video. But anyways, so I watched the video and they solved it very interestingly, using data structures such as a set and stuff like that. So I kind of want to regurgitate what I've learned to kind of shove in my head to kind of glue it so it stays. Well, that's how I learn. Um, so yeah, let's just go ahead and read the problem. So the n queens puzzle is a problem of placing n queens on an n by n chessboard such that no two queens attack each other. So basically, no queens attack each other at all. That's also one thing I didn't really understand. I think the wording's kind of weird to me. Where the chessboard such that no two queens attack each other, but in terms of n, right? I was thinking about like if n was 4, then only two queens can attack each other, and the two other cannot. I don't know. My brain's kind of weird, but that's how I thought about it. After watching the video, that kind of got my understanding correct. If it was an interview, I'd probably like ask if that was like a thing, if what I just explained was like the case. Um, but it's not. So we can just continue with the prompt. Given an integer n, return all distinct solutions of the n queens puzzle. You may return the answer in any order. Okay, cool. I don't think in any order. I think that's fine, but I feel like it's kind of like I don't know. It's kind of like giving too many options for the person to solve this problem, which is kind of like a negative. I don't know what the word is, but like it's like going to the opposite of the solution. I don't know what the word of that is. So each solution contains a distinct board configuration of n queens placement, where q is the queen and the dot is an empty space. So we're gonna go over the problem again, but let's just say that the input, just scrolling over the problem, we're given only an integer n, so int n, and then our output is going to be return all distinct solutions to the n queens puzzle. Um, you may return the answer in any order. Honestly, this is also a question you need to ask the interviewer with, because for me, what I would do is I would literally, because in the example, you see that you're given, and then the output is basically like a 2D list where each sublist is a configuration or the column of where the queens are. But if I was to do this in an interview, I wouldn't keep this in mind. I would just say, okay, so they want me to return all the boards that yeah, just return all the boards. But in this case, they just want you to return all the columns of where you place the queens, and then each element in the sublist represents the row. So as you can see here in this example, in the first configuration or the first result, the first like randomization you can, or the first combo you can do, it's basically row 1 where the queen's on column 2, and then the second element, the queen's in column 4, which is right here. And then the third element, the queen's in column 1, right here. And then the fourth element, which is the fourth row, the queen is in column 3. So we have to follow that. But yeah, so basically, so our output is going to be 2D list, where sublist elements equal to sublist elements equal to position of queen, where sublist at I is equal to dot sublist I contains This equals to empty space. Sublist at I contains Q, which equals to queen position, and then sublist, and then I is equal to the row of board. And we can say that sublist at I and J, where J equals to column, right? So that makes sense. List of sublists. So for example, is equal to like Q. See. So yeah, kind of explain what the output is in my own understanding of it, and kind of took like a lot of notes on how to whatever that is. Right. So I guess for some questions for the interviewer, other than the questions that I would have asked, I think it's good to also just get the minimum input and max output. So what is the min and max of n? Let me just scroll down. And then I guess can n be empty? Can n be 0? I guess that comes out with the first question. So let's just go and look. Scroll down. Let's see what our input and output is. I mean, what our min and max. So the min is 1, the max is 9. Yeah, so 1 min, 9 max. I think min 1, max 9. Yeah, that makes sense to me. And so now that we asked some questions, let's go over some examples, right? And I guess through some examples, we can also take some notes at the same time too. But I think, can I just, where's my print screen? Right, print screen right here. Okay, hopefully Excalibur lets me do this. Okay, cool. This is why I love Excalibur. It's so cool. So let's say our n is equal to 4, right? So there's only one example, but n is equal to 4. There could be multiple examples, but let's just do this. So n is equal to 4. That means we have a 4 by 4. Can I just do this? So 0, 1, 2, 3. 0, 1, 2, 3. So we have a 4 by 4 board basically. Um, and we need to place wherever the queens are. But let's say just ignore these queens for a second, the ones I'm crossing out. Just ignore those queens, right? Actually let's actually kind of take where those queens are, right? Just to make it easier. So if you don't know what a queen is, which I don't, a queen can move um like a queen can move in any direction, up, down, left, right, and then it can also go in diagonal. So yeah, it's kind of weird, but that's how it is. And it can go in that range infinitely, right? So that's one thing to note. Just take notes of that. So what is a queen? Queen, diag, infinite, horizontal, infinite, and then vertical, infinite. And from that, if we look at it in like a computer sciencey way, instead of saying horizontal, we can just say row. And then instead of saying vertical, we can say column, right? So it can be in this column, right? It move. I mean, it moves in this column, and I mean, it moves in this row, moves in this column infinitely, and it can move in diagonal infinitely too in both directions. Um, so yeah, that's kind of interesting. Um, so yeah, that is interesting. So going back to our notes, so it can move in either of those directions, row, column, diagonal infinitely. And so our whole task is to make it so that no queens, no other queens at all are in either of these directions that move infinitely, diagonal, column, row. So in this case, we can since I know that this is a backtracking problem, we can place a queen here, and then so we can place a queen here, right? But if we go at it in a human perspective, it's going to be very tedious to figure out where we can put this queen. But I guess in this way, we're like, okay, I'm gonna put this queen here. Um, I'm gonna put this queen here. So if I put this queen here, then the next queen in the next row, it can't be in the same row, obviously. It can't be the same column, obviously. And it can't be in the same diagonal, obviously. So if I basically draw out where, I basically draw out the directions of this queen, then that's where I'm not going to put the um the next queen in the row. So this queen's safe there. So that's cool. And so now what I can do is I can go to the next row and say, okay, since all these queens move in this direction, right? I think the only direction that's kind of useful is the diagonals in this case. So here, here, and then the column basically. And yeah. So it's safe to say that the only solution for this queen to go in this row is right here. Right? So that's cool. So now let's draw out all the rows and columns and diagonals of the direction of all the other queens and rows 0, 1, and 2 so we can place the queen in row 3. So we can't place the queen here on column 0. We can't place it in column 2. We can't place it in column 3. And if we look at the diagonals, they kind of match up, right? So the only column left, oh yeah, also take into account the diagonals too, right? So the only column we can put the queen in row 3 is column 1. So yeah. So to take away from that, you can tell, you can tell, so I guess we're in the matching phase as well. Um, I need to take a sip of water, actually. My throat was getting really dry. All right, I'm back. So we were in the matching phase of this. So, yeah. So where was I? Yeah, so the queen moves in horizontal, diagonal, and vertical, or it moves in diagonal, row, column. So, what we can say is that we can't place them in the same row, and we can't place them in the same column, and we can't place them in the same diagonal. So what we can do is we can make sets of those. So sets of column, row, and diag. For diagonal, I mean for column and row, that's kind of easy. But for diagonal, I didn't really know how to solve this. But in the video that I watched coding live with Larry and I watched LeetCode. And they both had the same idea where there is two diagonals. There is we just type it down. So there's going to be a positive and negative diagonal. So, um, pos diag, negative diag. So there's gonna be two types of diagonals. So for a positive diagonal, it's basically moving upwards, so like this, right? So let's say we start at 3, 0, 3, right? So no, row 3, column 0. So if we go up like this is a positive diagonal. And what you can see is if we do 3 plus 0, that's 3. That's 3. And then 2 plus 1, that's 3. 1 plus 2, that's 3. And 0 plus 3, that's 3. So that's a positive diagonal. We can do the same thing here. Was like 3 plus 1, that's 4. 2 plus 2, that's 4. 1 plus 3, that's 4, and so on. So those are our positive diagonals that we're going to keep track of. And then for negative diagonals, it's basically the opposite, where we do row minus column. So in this case, 0 minus 0, that's 0. 1 minus 1, that's 1. 2 minus 2, that's 0. 3 minus 3, that's 0. And then we can do like 1 minus 0, that's negative 1. 2 minus, oh wait, no, oops. We can do like 1 minus 0, that's 1. 2 minus 1, that's 1. 3 minus 2, that's 1. And we can do 0 minus 1, that's negative 1. 1 minus 2, that's negative 1. 2 minus 3, that's negative 1, and so on. So we just gotta keep notes of those. So I can just do this. This is easier. That's easier. Yeah, so, okay, cool. So, why is it OBS? I don't want to get OBS. Okay, cool. So pos diag will hold values of r plus c. Negative diag will hold values of r minus c. So yeah, in row and column, that's pretty basic. Okay, so now that we know of those sets, we can pretty much solve this in a backtracking way where we find every possible solution at every step. So in this case, in a 4x4 board with 4 queens, there's only 2 solutions where they tried every row column placement of the queen, and they found that these configurations were configurations that satisfied. So it's basically backtracking. So basically, they found out that row 0 column. I mean, if we put this queen here, then it solves it. But if we backtrack, so just eliminate all this, make the queen move here instead, which they did find a solution here. And so yeah, that's kind of basically it. So I've done backtracking problems before, so this kind of makes sense to me. So let's go ahead and kind of plan it out. So basically, we need to initialize sets. So we have a call set, row set, and a pause. Let's name it pause set and negative set. Okay. And then we're gonna populate those later on, and then we're going to have a resulting list. So res equal to that. And then they don't give us the board, so we have to make our board. So create board. So board is equal to let's make it empty first. But to make it empty, it's basically a string of dots times board size or times input, and then we're going to do it input times I in range all the way up to what input. And then we're gonna do that for search recursion basically. So what do you want to do? Um, so we're gonna do our recursion. I think in this case, it's very similar. We can just take the index we're at. I think index is fine. No, no, we're gonna get a board. We're gonna get a board, and then I think a board in the index. So a board and index. I think that's fine. Is that fine? I think just the board. But um we also need to go increment our index. So I think board and index is fine. Hmm. But do we really need to have a board if we're going to initialize sets and have that track for us? Hmm. Hmm. I do it's board and oh no no. 'Cause it depends on on the backtracking problem. Um, Let me think. I might need to actually have help on this one. So the board or I think either or is fine. I think for the index, it's basically what column I'm at right now. Hmm. I think the board's fine. The board's fine. I think just the board's fine. Board and row. I think board and row. That makes sense. Um, but maybe just row. I'm having a brain fart right now. That's also good. Okay, so let's go back to our. Okay, so basically, if we find a solution here, I mean, no, if we put it there, then we say row. We go to the next row. So I think row is fine. But I want to do board and row, but it doesn't really make sense because we're using column, row, and position, and I mean positive and negative to kind of determine where to put it. So I think that's fine. Yeah, for row. Um, we don't need the board, I think. No, I'm making the board, so I had to do the row. Okay. So board and row. Okay, cool. So, all right. Bro, I don't know. Um, I think I need help. I think I need to reference the video. I think I'm gonna do that. Yeah, so I was kind of right. It's just the row, because we can manipulate the entire row just by um yeah we can yeah okay got it. So, okay. So, and then we say our base case is if the row, if the row is more than equal to n, then we just we're going to add. So add all rows. So I'm gonna say let's say no, I'm gonna say add all rows into res. Add all rows into res as one list, which is just this input. And then return. And then there'll also be a going to be a base case where such that I was gonna check if if they're in either column or row or diagonal. So if if row, so if hmm, I think that's fine. So I think in this for loop I'm going to make I'm going to check for every column, right? So for column in range all the way up to n, right? All the way up to n. Check all possible columns with queen. So for this, I can say if if C if C and set, then I can say if R and set, and I can say if C and set, if C and set, R and set, or positive or diag and set, then just continue and move on to the next column, right? So I think R and set doesn't really matter. Um, yeah, R and set doesn't matter because we're doing R plus one. We're gonna go to the next row either way. Um, continue. Otherwise, if they're not in the set, then this is a possible position where we can put this queen. So, if not, if past case, then possible, then current is possible placement in queen. So then we're going to say that we're going to place the queen here. So we're going to call dot add. Let's see. Um, what dot add? I think we need a row actually. We need a row. And then diags dot add row column, whatever. Was it plus minus? Right. So yeah. And then we're going to say we're gonna go to the next row. Go next row. And then backtrack. So we say call that remove C, and diags dot remove R plus and minus C. So yeah. So basically we're going to place every queen in a possible position. And yeah. And then in the next row we're going to check if it satisfies a valid position and so on. And then in the end, what we're going to do is we're just going to call row at 0. We're going to go to the first row and then return res. And so yeah. So yeah, we also need to update the row. So how do I say this? So I'm pretty sure um I'm pretty sure what this does. So board at R and C is equal to a queen. Yeah. Okay. And then we have to say the same thing here, but backtrack, so equals to a dot still. So this is backtracking. So yeah, so if we code this out, it should work. So first step is to initialize our sets and to create a board. So call, should have copy. So call is equal to empty set. Pause is equal to set. Negative is equal to set. And our board, let's create our board. So this comprehension. So our board is just going to be a sublist of periods times n, right? For in range all the way up to n. Okay. And then we can go ahead and code our backtrack our recursion. So DFS, going to take in just R. And then we want to check for our base case where it's completed. So if R is more than equal to n, that means we kind of reached the end. We can't go 5. I mean, we can't go since it's 0 indexed. If it's 3, then we're in the board. If it's 4, then we're out of the board, meaning that we reach the length of we reach out of bounds. So that means that we're good. And so then if so if we reach the solution, we kind of just have to append it. So I'm going to say that res append. We're going to append the board. It has to be in a single list.
Replacement fee, but it's already shipped and cannot be canceled. For details, go to your orders on MC.
That's kind of scary. Um, so we're going to append we're going to append everything in a single list. So that join. So we're going to add a string for every element for every row in board. Yeah, I think that works, right? That join for row and board. So this should say that we're going to add a string. Yeah, yeah, that makes sense. Okay. It's gonna be in the list. Okay, cool. So yeah. Okay. So now we got that, and then we have to say just return. We're going to basically check. We need to go through our for column in range of n. we're gonna place it in every position. So, but we have to first say, um, so if C in set, if C in column, or C in column, or I like doing it like this. So if C in col, or yeah, this is I like this. I think this is like a yeah, I just like how this looks. So if C in column or let's say positive, so R plus C in R plus C in pos, or R minus C in negative, um, then just continue. This looks weird, but like it just makes sense to me. Okay, but if that's not the case, or I can just say like this. Can I do like this? Continue. Yeah. Um, that's kind of ugly, but that makes sense. That looks really ugly. I don't know. But maybe if it was like, I don't know. I don't know. Okay, so if that's not the case, then we just add it to we just add it in that position. So call add C and then pause that add R plus C, then negative add R minus C, and then we go to the next row. And then we do backtracking. So call dot remove C, positive dot remove R plus C, negative move R minus C. And then I forgot we have to change that, add that queen in that position. So board at R and C is equal to a queen. And then here, we do the opposite. We just remove it. This is backtracking. So yeah. And then we got to call depth for search at 0, and return res. Then it should run. Oh, oops. Or I didn't even add res equal to end list. Oh, happened? What happened here? I don't know what's going on. That's so funny. I don't know what's going on. Um, Interesting. I think it's dot join. Yeah. Um, how do I do this? So I want to add the whole row. Um, my Python skills are kind of depreciating. Okay, so res is empty, and I want to add I want to add the whole board. So let me make it simple. So temp is equal to a list, right? And so in that list, I want it to look like this, where it's a list of strings. So think that join, right? Um, can I just say like I want to join whatever I'm given? Hmm. I want to basically get, how do I do that? Oh, join row. Okay, I had a brain fart there. That makes sense. Okay, so submit, and it's a working solution. So yeah, this problem was so hard. Oh my god. So time complexity, 2 to the n. So you have to go through every solution, or every possible case. Um, so yeah, I had a lot of problem with this problem because like I don't know, backtracking is not my go-to. Like, this was 40 minutes. Oh my god. So yeah. That's pretty much it. I think I'm happy I'm done with backtracking, but I know it's always gonna haunt me, but I should just continue improving on other skills. Because I feel like time will improve my skills with backtracking the more I uh deal with it in the future. Because I'll be like, because maybe like 6 months down the line, like, oh, this is a backtracking problem. I've done problems like this before. So I'm not that new to it, but I can uh probably do it easier or even better now that in the past I've done it before and stuff like that. But I think I just need to continue on my other skills such as what graphs. I need to relearn graphs again. Trees I'm fine at. I've done a hella tree problems, so I'm pretty sure I can solve a tree problem pretty easily now, or easier than before. Because I've done them a lot. So I think it'll be the same with backtracking, but it'll be harder than trees because trees were easy for me to grasp, but backtracking was not. But once you understand the patterns by doing these problems a lot, it gets easier. So yeah, whatever. It's a lot of errors in this one.